Okay, today we're going to learn about residuals, see if we can understand all these four graphs that normally show up when we're doing regression analysis. And I have divided these in several parts so that we have smaller pieces at the time to master. So the first thing I want to clarify is the direct difference between correlation and regression. In correlation, we look at the relationship between two variables without knowing the direction or the influence one variable may have on the other, and correlation happens in many cases for things that we don't know what they're related. But in regression, we are trying to predict the outcome of one variable from one or more predictor variables or other variables. If you have one predictor or one variable explaining another one, then we call a simple regression. If we have more than one predictor, we have multiple regressions. And introductory statistics courses we normally just cover simple linear regression. That means one variable is trying to predict the other variable. In the prediction part is when we start need to understand the residuals. So before we start fitting any predictive model to two variables, I want to emphasize on George Box's motto: all models are wrong, but some are useful. If we need to part from this idea so that we can understand what will be the most useful of all the wrong models, kind of thing. And so we can look at details, and sometimes there is a lot of gray area in there, and there may be even disagreement between people looking at the same models, but that's part of statistics in many cases. So here we're going to learn the tools for understanding what will be maybe one of the best models. Fitting a predictive model, one way to understand this is the idea of the signal and the noise. And the idea of the signal and noise is perhaps the most fundamental conceptual model for reasoning statistically. And this is, I think, first coined by Connell and Polasek. And what does it mean, the signal and the noise? Another way statisticians call it sometimes the deterministic and the stochastic aspect of it. So the signal is an interpretation of the mean. For example, imagine we have a gold nugget and then we try to weight it. And if we weight it 100 times, we want to see what will be the actual weight of the nugget. We may have a little bit of variation from weight to weight because there is random variations in the weight, because the way we look at the scale, there may be some variations, but we want to establish this unknown value of the weight of the nugget from some measurements. And so the signal will be the actual value of the weight of the nugget, and the noise is this random variation that may occur by the different ways to measure it, to weigh it. Another example from the signal and the noise that's very clear to understand is that astronomers in the beginning, they were not, when they were measuring the distance to the stars, they were working in isolation, and they didn't want to talk to other astronomers because they didn't want the errors to be adapted with the other errors, because every day they measure, they have a slightly different measurement, and so they wanted to keep the errors to the minimum. However, when the astronomers start considering, okay, let's add up these numbers and put them together, not add up, but basically combine the data, what they find out was a very distinct signal, a measurement that was strikingly consistent through all the measurements, and there was some errors, but they were minimized by the adding all of them, by putting together all these data points. So the signal becomes more prominent the more data points sometimes we have. And so the signal and the noise is an interpretation for the data. For example, if you have a regression analysis and we try to see the signal here, we can see overall there is some kind of trend going up, and there is some concentration here in the middle, but then you go to the borders here, to the edges, and there is a lot more scattered more variability in here and more, so the signal will be here in the center and this is the scatters. Sometimes it's a lot more obvious, like in this case where the data is very concentrated, there is the signal is more strong, and then we have some noise which is a little bit out of this main line here. This is clustering there. So another way to understand the signal and the noise is if you have some kind of pattern here, like this may be seen in over time in the stock market or weather or something like that, and we want to see the signal that something is a train going down, but all this noise sometimes is hard to understand that signal. So the signal is separating the essence of what's happening from the noise. That's the idea of the signal of the noise. And it became more famous with Ned Silver wrote his book, The Signal and the Noise. So let's start for understanding the height. So we can see there is a lot of noise per se, a lot of variability on the height, which is measured in inches in here. And the mean here will be the most basic model, basically the average of all these points. Can we use the average to predict somebody's height in inches? And in here, we can see that this average is missing a lot of these points in the edges here, yes, and this is a lot of the concentration here, so maybe okay, but there is a lot of variability which is not explained by this average. So in regression, we're trying to see if there is anything else we can use to predict the height instead of just the average. And we see the age in years here may have maybe a good predictor. And how do we know that? Well, we can see a trend here and some kind of signaling going on, but particularly I want to mention and pay attention to the fact that the points that were here on the variability on the height is still the same points. If you notice 53, still 53 there, these 2 points here, these 2 points there, they are not changing the Y variability at all. It's just somewhere that is moved, taking in consideration the age. And we're going to understand what does it mean when they move this way, whether actually why they move. And for example, if you see the same graph, the same data, now here in gaps from 65 to 7 years old, we notice there is a distribution here, but there is lower than here and here and here. So we can see that every single group here has a particular distribution and tends to be higher as the years go by. So at the same time, not only go higher, each of them have their own distribution. And this is important also when we study regression, that sometimes in the textbook we only see 3 or 4 data points, or maybe 10 data points, and that's hard to understand that each of these values have a distribution in itself, and therefore we're going to look at that. And now, if we look at the average of each of these, we can see we can explain or model this age group by this average and this age model by this average, and so on and so forth. And so the regression line will be the signal that's trying to capture all those averages, yes? And how is that signal being produced? We're going to learn that. And then the noise is whatever is not captured by that line. So we're going to, the line is produced by the least square regression. It's called the least square regression line, and it's produced by minimizing the square distances. We'll see that in a second in the next slide. Represents the best estimate of the true signal, yes? And here we see this is from each data points we can do a line, a red line to the regression line, least square regression line, and we can see there is distance in there, yes? And then those distances can become squares because the same size in each side, yes, from the distance. So basically the least square regression line is a line that minimizes the square distance to this line. So if you move this line to different places, the squares will maybe be bigger. But this is the smallest possible, even though you see some squares here that are bigger. This is the smallest overall on average of that. That's how the least square regression line is produced. So let's look a little bit of this line here. So let's look at the residuals or errors. Errors and these residuals are used interchangeable, and error sometimes seems like there is a mistake, but in reality it's not really a mistake, it's something what is left over, but it's used interchangeable, so I prefer a little bit slightly more to say the word residual. So let's take for an example a value like 32.6. That value has an observed x value 32.6 and also has an observed y value, and so then we see that the same 32.6, it touches the line at this point. Yes. Now this y value is the predicted value for the same x. So for every x we have in here, we have a predicted value. But for every observed x, we have a y, and we also have a predicted y. And that part between the observed y and the predicted y is the error. Notice that the x is constant in here. The x doesn't have any, well, it has to do because we're looking for that particular x. But basically, what we're looking at the residual is only the distance between the observed y and the predicted y. So that's the residual of the error that we are going to be analyzing. And there is one of those for each of the data points. So we have seen these 4 plots. We're going to try to explain each of them in details. Please feel free to ask me questions once you finish this series of presentations, and I can try to clarify even further. So the usefulness of residual plots. Analyzing the residual plots help assess whether the observations, the observed errors, is consistent with the unpredictable errors. So observed errors and unpredictable errors are sometimes hard to understand. We want to be consistent. So what do we mean by that? First of all, we need to understand what is an observed error, which I just showed you a second ago. And now we're going to understand what is unpredictable error. And so let's give an example of a tossing a die. When we toss a dice, we know the probability distribution is that every single face of the dice have the same probability of being coming up, so it's 0.1666. But if we toss the dice actually and do an experiment and toss it, say 100 times or 200 times, we can see that there is some variability here, yes? And they are not exactly in the perfect line like we see here, but there is some unpredictable errors. And they are okay, they are random errors. It's another way to say unpredictable errors would be random errors. They are not too far away from what is expected, so we will live with that, unpredictable errors. But overall, we can say a consistency of all the numbers come in equal amount of time. However, if you see something in which the number 6 and number 5 come consistently higher than the other numbers, a lot more, some of them maybe by twice as much, like in this case between the 6 and the 4, we may suspect there is something wrong with this die. And there is things to do with it. That's what we're trying to do with the residual analysis. We're trying to see if we are like something unpredictable, something random, or something that may be an alert, something we need to do something about. If you were a gambler, maybe you will adjust your gambling to gamble for the 6 more than other numbers. And if you are trying to get the dice to be all without being biased, maybe you need to adjust the process of producing those dice. So understanding this is always very important, and the main point of this part is I wanted to make clear that in residuals we're trying to understand those observed errors if they match some unpredictable errors. So to summarize this part, we start with the premise that all models are wrong but some are useful. We understand what is achieved by fitting a model, understand how the least square regression line is one model that captures the signal or the mean, understand that there will be errors, noise, or deviations that is not captured by the least square regression line or the model. Understand that the residual plots will help us understand if the noise or the error